Hello everyone, in this live session we're going to use video direct memory access, that is VDMA, in our block design. So VDMA is used to access DDR memory in our Zynq processing system architecture. So VDMA is a specialized form of DMA that is specifically targeted for video processing systems. So now in this project we're going to add VDMA. It's very easy to use. Add and source VDMA. You're only going to see one AXI video direct memory access. We're going to add this. So the VDMA needs to be controlled by the Zynq processing system, and again the VDMA controls the DDR. So we're going to require an additional AXI interconnect. This interconnect will be master for the DDR and slave for AXI VDMA. It will have two slave interfaces and one master interface and two slave interface. Okay. This master interface will be connected to the high performance port of Zynq processing system. And let's go to the Zynq processing system. PSPL configuration, HP slave AXI interfaces. Check HP0 interface and it will add HP0 interface. Connect this AXI interconnect M0 AXI to HP0 port. Connect clock to the clocking wizard. Now AXI VDMA has two AXI interfaces, one for memory map to stream and another for stream to memory map. Connect both of these to the slave interface of AXI interconnect. This AXI VDMA has an SAXI Lite interface to control this. We will control it through PS. So the PS is master to this AXI interconnect. We will require one more additional master interface in this AXI interconnect. Connect to our VDMA. So we'll connect this additional master interface to our VDMA. We're going to disconnect this TPGA connection to AXI4 stream to video out. We're going to insert this VDMA between our TPG IP and AXI4 stream to video out. So how the process works will be TPG will generate test patterns, and those test patterns video data is sent to DDR memory through VDMA. So VDMA saves that data to DDR. It will work. We're going to make it work in triple frame buffer. That means 3 frame buffers will be saved in the DDR, and when 3 frame buffers is saved, then it will again retrieve the data from those frame buffers and pass it to AXI4 stream to video out, so that AXI4 stream video out can display on the display device. We'll connect M-axis MM2S to video in of AXI4 stream to video out, and S-axis S2mm of VDMA to the output of PTPG. We're going to connect the rest of the clock. So this AXI interconnect will have one more clock and reset signals for additional master AXI that we just added now. Connect this clock to the clocking wizard and this resetion to the peripheral resetion. Going to connect this resetion to the peripheral resetion. Connect all these clocks to the clocking wizard. Holding down the control button, you can select all at once and then connect them to the clocking wizard. For this AXI interconnect, you will get clock from interconnect, get from clock from clocking wizard. Resetion will be from interconnect A resetion, and these other clocks will be from clocking wizard, while the resetion S0 A resetion, S01 A resetion will be from peripheral, then resetion. So it's connected. Now we're going to regenerate our layout. Let's see if any connections. There is no pop-up for run auto connection. That means we have connected all requirements. So let's go to the AXI VDMA settings to see some of its settings. So address width will be 32. It will be run in 3 frame buffers. 3 frame buffers is usually one frame buffer is adequate, but sometimes you can see tearing on the screen. So we use 3 frame buffers so that no tearing will occur. So we have enabled both read and write channel. We can auto the memory map data width for write channel. It will read the incoming signal and adjust by itself. And for the stream, the only thing that we require to change is stream data width to 24, because our XF4 stream to video out IP takes the input of 24 bit width. This stream data width auto will change to 24 as it is receiving a 24 bit input from TPZ. So now one of the important thing or using DMA to access the DDR is managing the addresses. It requires an address in DDR to save the data. So we go to the address editor. As you can see, EXA VDMA has two data mm2s and data s2mm with on-map slaves. We'll again auto assign, and as you can see, the offset addresses and high addresses has been assigned, and the range of this DDR is 512 MB because that is the capacity available in our Z board. According to board, we can even go higher if other boards has higher capacity DDR memory. Now we're going to validate the design. The design is validated, no errors. So we have already wrapped our block design with HDL wrapper in a previous lab, and constraint is also added. We do not require to add any further. Now let's generate the hardware, and let's go to the SDK portions. We're going to click generate bit stream, save the block design, and as the synthesis and implementation has been outdated, as we have added additional IP blocks, we're going to click yes, so it will resynthesize and implement and then generate bit stream. This again will take some time. We'll be back again when the bit stream is generated and export the hardware to the SDK and program our DMA. Just make it in the background and come back again when the bit stream has been generated.